structure of the body. This is a really fun talk. Did anyone come to see this? It was probably like a year and a half ago. I
think so.
Right?
I think so.
It's a really, really cool topic because we are not taught at all how the body is structured. In chiropractic school, you take a class called spinal biomechanics, like right away. Orthopedic surgeons take this class. You go to med school, you go to chiropractic school. You learn about the anatomy of the body, and they talk about the muscles, the ligaments, the tendons, and all the bones and how they work together. And all the models they teach us are completely wrong. And they're still taught this way over and over and over again. It's a mechanistic way of looking at the body. So for example, how do you guys think the spine is built? Most people think it's like a block, and then you have a little bit of cartilage, right? And then a block.
Yeah.
And then cartilage and a block, cartilage and a block. So you think of it like a block on top of a block on top of a block, and when you stand up, those blocks just squish together, they're on top of each other, right? Or if you think of a leg, you have your femur that comes down, and you got the tibia that connects to it, kind of like this, right? And you got this layer of cartilage in between. So what happens when I'm running? Squish, 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 squish. And you've heard this before, you get arthritis, that cartilage wears down, and then you go running, what happens?
Bone on bone.
So let's use that, let's write that on here. How many times have you guys heard this? Bone. Okay. This is a completely wrong model. It's almost impossible to have something called bone on bone. It doesn't happen. Okay? And we'll talk about this guy here, Dr. Stephen Levin, who was an orthopedic surgeon who pretty much proved that. He's the one that got into this thing called biotensegrity, big fancy word we'll get into. But essentially he would do surgeries on people, orthopedic surgeon, do surgeries on their knee, people who had bone on bone, and he would open it up, and guess what? The knee would be floating. It wouldn't be touching each other at all. The bones would be floating next to each other. Same with the spine. You look at the spine, the bones were never touching each other. They would always be floating, even if all the cartilage was worn away. Those bones actually float. And we'll talk about it. Okay? What's that?
Where do you pain then? If they say it's bone on bone and you're pain.
So we'll ask that question later, and we'll get into that, okay? Then there's something called unidirectional versus omnidirectional. Unidirectional means this. A house is built unidirectionally. So if I take a house and I have it upright like this, it's good. If I take a house and I lean it a little bit, what happens to the house? It'll collapse on itself. Okay? This is a big thing. I'm going to show you this picture here. A couple of problems with this model. Statue. I can have a statue exactly the same size as me, same weight as me, just a perfect replica of my body. If I tilt it on its side, guess what happens to that statue? It actually breaks in half. It can't hold itself up. It's called unidirectional. If the spine was built this way and the legs were built this way and we were built in this manner, just blocks stacking on top, as soon as you do this, boom, you crack right in half. Okay? Anybody know what this is over here? Anyone know what kind of dinosaur?
Wait, hold on. Give me 1 minute.
Brontosaurus. Oh, I guess it could be a bracket. I don't know. Who knows, right? Who knows the dinosaurs even exist?
So we asked the question and doesn't know the answer.
The answer is no one knows, guys. Come on. So look how long this thing's neck is. Now here's the thing. We don't think about it, but this is not proper. This could never happen if it was like this, if we were built this way. I want you to think about this. If you had something super heavy sticking way out like that, you need a counterweight way above it to hold it back. And it doesn't have it. Okay? This is our modern day Brontosaurus. What's that? You guys know what that is?
Ostrich.
No one knows.
Emu.
Yeah, maybe it's an emu. You guys don't know. That's an ostrich, right? Look at that neck. Look at the structure of that neck. Do you think that's just block on top of block on top of block?
No way.
Or is it very complex? Super complex, right? So what we're taught is this mechanistic model that we know is completely wrong, okay? So along comes this guy named Buckminster Fuller. Everyone heard of Buckminster Fuller before? And he creates this whole new type of architecture. Now, he has nothing to do with the human body or anything like that, but one day he's thinking about the earth, and he's thinking about the sun and the moon and how they suspend above the earth, almost like they're connected to it, yet they're not connected to it. And it sparks him on this whole new type of construction that he coined the term tensegrity. Tensegrity is a combination of two words. Guys are good. Tensegrity. So what it means is it's a structure that the more pressure you put on it, the more integrity it gets, the stronger it gets. Versus like a house, the more I press in on the walls of a house, what happens to it? It's going to collapse and break down. So he decides, wow, there's a new structure that we can build. If we press on it, it actually gets stronger and stronger and stronger and more durable. And you guys will recognize it. Let's show you some pictures of them. Pretty cool little structure, right? Okay. Anyone seen that before? What's that called? Right. It's called like spaceship something or other. Spaceship Earth. Thank you. Right? And you guys see the walls, see these little shapes inside of there, right? Now, what happens is these things, I'm going to show you a picture of this, but essentially there's tension wires keeping all of this together. What keeps this together are like these elastic bands, and the more that you press on it, the tighter the elastic gets, and the stronger it gets. And you can start making some really neat little structures, such as this. If you guys can see this, it's a tower that goes all the way up. Now you see it looking underneath it, looking up at it. Pretty neat looking, right? Mm-hmm. Anyone heard of something called sacred geometry before? All living things have a sacred geometry. Here's the neat thing. See these bars? None of them are touching each other. They're all put in place by these suspension wires in between. So if you look at this picture, you see all these bars, none of them are touching each other, and they're going straight up, higher and higher and higher. What's so cool about this stuff is the material you make is extremely light. I'm going to show you this structure in a second. It's rubber bands and pencils. That's it, and it makes a really solid structure. I don't want to press it too much because it will. But compared to, think about it, it's literally 6 pencils and 6 rubber bands. And you can make this amazing structure with it, right? It's pretty neat. I don't want to break it because I got to do some demos with it. And then again, you got some arts and things like that that are pretty neat. And
where's that on that?
What's that?
Do you know the name of that thing?
No, I'm sure you can look it up, right? And there's guys who specialize, they do art with this tensegrity. Okay. Yeah, you can see the star in it, right? Pretty cool. And a lot of people talk about this, like it's, the Jewish star, the 6-sided star, like this. It's really important in sacred geometry. And this is the reason why. It's kind of what we're going to talk about, the basic structure of all human life. Every cell of your being, every piece of DNA is that structure. So again, it goes on to this. This one guy, orthopedic surgeon in the 70s, is working on people and realizing, like, wow, what we're taught isn't true. There's no way the spine is like that, because if I tilt this way, something bad's going to happen. If I take a brontosaurus, like that neck that's sticking way out there, it would just crumble to pieces. There's no way this is true. So he starts looking at architecture for inspiration, and he comes across things like this. And in fact, it was saying he was looking at, I think, a building, and he saw one of these models that was like this. And that right then and there, he had the idea. It's like, wow, this must be what's true of the human body. And he started researching it more and more and more. And now I'm going to show you some really cool models of how this is the truth of how we are structurally made, okay? So, now it's time for the fun little demo thing. I'm going to pass this around if you guys are brave enough. You guys see this structure? This is the basic structure of every cell of your being. Of all living things, it's made up in this structure. Do you see the star?
Yeah.
Can you see it? You guys are seeing it?
Whoa.
Right? You guys see it mostly from a different angle?
Yep.
Okay. What's crazy about this, when you look at these cells, so if we're talking about the human body on a big form, these pencils would represent the bones of your body, and the rubber bands would be all your muscles and ligaments and tendons. Everything suspends. As this compresses, look what happens. No bone on bone, right? Everything is suspended. Every bone in your body is literally suspended. Now if you take this down to a cellular level, this would be what the cell looks like. The cell has all these little strings, like suspension-like things inside of them that contain it. And then just picture like a little covering over everything. That's what a cell would be. Now I want you guys to picture one of these, but smaller, in the middle of this thing. What would that be? That would be the nucleus of the cell. Okay? So the nucleus of the cell would be inside, and you'd have wires attached to the nucleus as well. Here's what's cool about this item. If I just take this thing right here and I move it like this, every aspect of this thing changes. So if I'm in a house and I step right on the ground at this house, there's only one part of the house that's being affected, where I'm stepping. If I take a structure like this and I put one little pressure on this little part of that bone over there, look at the other side. See it compensating and moving right away with it? So now I want you to think about the nucleus inside of there attached by some more wires. If I do that, what happens to the nucleus? Now inside the nucleus, what's inside the nucleus? Inside the nucleus is DNA. And what's the structure of DNA? You guys heard of a double helix? So what's really crazy is this, guys, is one of these stacked on top of each other. So 1, 1, 1, 1. If you take two of them, so if you take another one of these, put it next to it, and you make a tower with it, it's a double helix. That's what it is. So I want you to realize, in real life, you can't make one of these. This is only a model because, see this unit right here? You guys see this string right here? Now I want you to imagine, instead of it being a string, I want you to imagine a string of pearls or something like that, little beads. Now I want you to picture every little bead on there is one of these.
Oh.
That's really what it is. It's just life is this unit smaller and larger.
Whoa.
So if this is a cell, and you connect a whole bunch of cells together, what do we call a whole bunch of cells connected together? Well, we call it first a tissue. A whole bunch of cells together, let's say you get like a muscle tissue or something like that, an organ tissue. A bunch of tissues together, you get organs. A bunch of organs together, you get your organism. That's what this is. So we can talk about this on a really big scale, like the whole human body, like we're going to, or an extremely small scale, like the DNA inside of this thing. Does that make sense? Pretty crazy, right? This is all we are, just this, times a lot of them. Different sizes and what of them, too. Just to show you some examples, this is what I have in my hand. Hey, let's pass this around. If you guys want, easy way to do it is just take the pencils and just try to even them out a little bit like that. And then just squish it a little bit, play with it. Don't be the person that breaks it. First one, boom. Okay, this is what I'm talking about. This is that same structure, but look what's inside of it. But there's other strings going to it as well. That's the nucleus. You can't affect one part of this thing without affecting the nucleus of that. Make sense?
Did you put that nucleus in this one?
What's that?
Did you put the nucleus in this one?
No. If I made a smaller one of those, Joey, and you placed it inside of there and connected it with rubber bands, that's what it would be like.
So it's like micro to macro, basically.
You can keep smaller, you can get bigger, forever and ever and ever. Okay, that's what life is. You guys see this? What's it look like? You guys see that? This is like just a model of what a virus looks like. Now, these are separate pictures. I didn't type in like virus tensegrity. This is just what they think a virus looks like. You guys see the shape of it? Remember this guy? This is, the next picture is something, I think it's called Vovox. It's an algae that grows on top of ponds. You guys see the similarities of that? If you get really close to it, if you guys want to come look later, it's even got the little pictures and the little lines that you can see inside of there.
Wow.
See dandelion?
Figure this out.
It's pretty crazy, right? On different levels, there's blowfish too, right? Oh, pretty cool, right? Now here's the cool thing. You start looking at this model and you start to see how the human body is built, putting these pieces together. So this is what a human spine, a model of a human spine, what it actually looks like. So when you see it, the bones are the solid little circles and things like that, and these are all the muscles, ligaments, and tendons inside of there. Okay? So this is the human body. I can also show you guys, this is what a human pelvis looks like. This is a model of what the human pelvis is like. Okay? Pretty neat, right? Let's show you guys one more thing. It's a video showing you just a model of the foot and leg. So you see all the tension wires in that, guys, and how you affect one little thing. He's only pressing one little area. Every little part of that thing is being affected.
How come you didn't bring that?
Look at the toes.
I started working on that. Sorry. Pretty neat, right? I want you guys to realize that's pretty much just a whole bunch of popsicle sticks with some elastic bands. Think about how light that is, the material is, and how strong it actually becomes and how durable it becomes. How flexible it becomes, too. And that's pretty advanced stuff right there, huh?
When you think about it, it's actually pretty simple, but it's just a bunch of, like, pulleys.
So, pretty neat. So, anybody have any questions so far? It's gonna be a pretty quick, fun little talk today, but let's talk about this little guy over here. And I want you to relate this to the human body, especially the back and the spine, right? Because a lot of times people come in, let's say they have knee pain, or they have foot pain, or something like that, and we're adjusting them at their neck, and they're like, what the heck are you doing? What does this have to do with knee pain, neck pain, things like that? I want you guys to realize, because of this, you can have pain anywhere in your body, and the issue can be somewhere completely different. You have no clue what's going on. Okay? So, right here, let's say I have my atlas, my axis. Anyone know what attaches there? You have some pretty big muscles that come up and attach to those points. Yeah, you got your things called your trapezius muscles. So remember, these are like the sticks, or I'm like the pencils, and the things in red that I'm drawing are the suspension wires. So you have your traps that come down just like this. Make sense? Everyone knows what muscles I'm talking about? Ones that usually hurt on people somewhere? Okay. Now here's the deal. Every wire is connected into itself. So here's the deal. I have these muscles here. I also have this other big group of muscles that come this way. Anyone know what these are called? The latissimus. Anyone heard of the latissimus dorsi?
Yes.
Your lats. They come this way. And they actually integrate all together. They're all connected, interlaced. Okay. Now you also have some muscles that come from here to here, to your spine. Anyone know what these are called? These are called your rhomboids. They're the ones that squeeze you together like this. Squeeze your shoulders together. Now when you get to your low back, you have these things called multifidus. Things like these muscles, these strong back muscles down here that go into this area. Now what are these called? Muscles that come from here to here. Above that, right where this is. Called your glutes, guys.
Oh, yeah. Those ones.
Right? So you have your glutes over here, and they kind of insert down here too. And then you have what Sean said, another group called your hamstrings that come all the way down here. You guys follow me so far? And then what connects from here down to here? Your calf, called your gastrocnemius muscle. And then you got these little teeny muscles down here and tendons and ligaments that connect to your toes. Pretty cool, right? We got other muscles, we can do on the arms too. Now I want you guys to realize something. When you have an atlas subluxation, top bone of your neck goes either to one side and it goes forward and it twists your body. So let's say you come in here and you twist this bone this way. So it goes up, corkscrewed up this way. What's going to happen to this muscle fiber? It's going to pull, right? And it's going to constrict this one. Okay. What's it going to feel like here? A pulling away from your muscle. So do you guys see how a top bone here, out of place, can cause pain right there? Here's the problem though. Just like that model. Can I see that model? Who has that model? What if I see it real quick? Hope I don't break it so everyone can play with it. If I take this top one, let's say a bone here, and I move it this way, am I only affecting just that area or every little aspect of it? Everything is connected, so.
I'm done.
Joy? Everyone's all right? So.
The one broken.
Not yet. So, this muscle is going to get really tight. Now here's the problem. What's going to happen to this muscle? It's going to pull as well. Wow, could it pull this bone out of place, possibly, or put tension on it? What's going to happen to your spine? Is it going to stay erect? Or is it going to start to pull one direction?
Yes.
Right? What's going to happen to the disc in between these areas now? You've got the shearing force pulling on that thing all the time. Right? It's going to cause more and more damage to that area. Oh yeah, by the way, it's connected to here and here too. What's going to happen? Let's say it pulls this bone this way. What's going to happen to this muscle fiber? Going to get tight. Makes sense? It's going to, as this gets tight, it's going to pull this up, which is going to pull your whole leg up. You think why we look at your leg length when we're checking to see if your atlas is out. It'll pull one side up. Okay? This gets tight, this gets tight, this gets tight. What's going to happen to your foot in that side? It might pull everything really tight inside your foot. Okay? Every little thing is connected inside of you. Right? Literally, you could have a dislocated finger, and that could be causing your knee pain on the exact opposite side. That's how complicated this whole thing is. Okay? That's how amazing the structure of your body is there too. What's so cool about this too is, you know, we always talk about the nervous system as the master controller and how the body communicates with itself, and that's only partially true. Okay? The nervous system, what's really cool about it is, think about what the nerves control all of the tension wires on here. So if you get pulling here, your nervous system can react and have you adapt and balance out in a lot of ways. But here's the other cool thing about the human body. We talk about communication between cells. The model doesn't make sense. The nervous system model doesn't make sense. Meaning, my brain, if something's happening in my elbow over here, my brain doesn't send messages down to my toe and tell it what's going on. The body actually communicates much faster. And that's because as soon as something is pulling on my elbow over here, what's happening to my foot? As soon as, exactly, it's moving with it. You guys can understand that. As soon as my elbow moves, what's happening to my toe over here? It's moving literally at the same exact time. You literally have instant communication inside your body. Every cell of your body knows what's going on in every other cell of your body instantly because they're all connected. You can't move one without moving every other one. Okay? Is that exciting to you guys at all? No. I think it's pretty cool. I'm just a nerd though, I guess. Also, this shows why we have injuries to certain parts of our body. You ever wonder why that athlete in high school was running and all of a sudden their ACL just blows out? It's a little ligament inside of your knee. So again, if I'm over here and I start pulling this way, a couple of these wires start to have a lot of tension on them. If I'm distorted enough, and then you do that one little thing, what happens when that wire snaps? That's your ACL tear. So you can literally be running with one, like let's say this bone's moved out and this right leg is up and this knee is being stretched apart and this little ligament like that is being pulled like that. And you do that one little thing and it snaps that whole thing. And life is not good after that, okay? So that's how injuries happen. Or same thing here. That's going out one way. You're getting pulling on your shoulder, and your shoulder is going to be torn, and then all of a sudden you do that one little lift and you tear your rotator cuff, for example. Okay? So again, just because you have pain or a tear here does not mean that's where your problem is coming from. Do you guys all see that now? Okay. How about this? What happens when you have surgery?
They cut the muscles.
If you cut an area, what happens if you have surgery? If you have spinal surgery, for example, and you go in and they cut all the tendons or they cut the spinal process off where it all connects, right? Life is not good. You guys know what happens if I snap one of these wires? The whole structure collapses. The whole integrity, the whole thing collapses. So as soon as you go in, you start cutting ligaments, tendons away, things like that. You're not just affecting that area, you're affecting literally every cell of your body. But even bigger than that, guys, think about your DNA of all your cells. Remember, your DNA is literally just a bunch of blueprints inside of you that are rolled up and put away, and your body doesn't make them unless it opens them up, right? The more you move and the way this is contorted will change what DNA is being expressed inside of you, okay? So what it means is that if my posture is upright and I'm moving a lot, my DNA is doing one thing, versus if this is the structure of my body, what's happening to the nucleus inside of there? What's happening to the DNA inside of that? It's all being pulled and distorted in different ways. Does that make sense, guys? So literally, no matter what you do, if you ever have a surgery, if you ever have an injury or things like that, if you go for a run, if you stretch, if you open up, you're changing literally every bit of DNA inside of you. Every movement that you make. Okay? Pretty cool. Okay? So a big lesson of today, it's a pretty quick, easy talk, I think, but a big thing we want to learn today is to start taking care of these tension wires too. These muscles and these ligaments. So, anyone know what causes these things to bind up? What happens if these start to bind up like that? You guys see what happens? This would be binding of a ligament or a muscle.
Wait, what does that mean, binding?
So like you ever have like a knot in your muscle?
Oh, okay.
So what happens is a shortening of the muscle fiber, and it gets there. It causes compression everywhere. So anyone know what causes compression like that, or causes these muscles to knot up? Yeah, did you not? Did you like that? Well, very good. You're smart. Acid. So number one thing are acids inside the body. And the reason for that are acids are positively charged molecules that cause a binding. They cause things to bind together. So they'll literally take these threads and these ligaments and cause them to actually kind of get closer together and closer together and closer together. Okay? So how do we get acids inside of us? Yeah, typically the foods that we eat. So we got our meats, our dairies, eggs, processed food. What else?
Sugar, oils.
Yeah, sugar by itself, not, but it's processed, yes. Yeah. What else? Alcohol. Medication. So do we have acid inside of us? The average American has a ton of acid inside of them. You have to start getting out. Okay? You guys may notice this when you start doing fasting, how much more loose you become. You guys ever notice that?
Oh yeah.
It's a cool little test. And before a fast, I kind of just see how far you can stretch. And then by day 3, see how far you can stretch. You'll be amazed at how much more you can go. You're getting acids outside of your body. Okay? This goes back to Prem, what you said too. Prem asked, well, if it's not bone on bone, how do we get pain inside of there? What I'm saying is this. The cushion might wear out, and the bones may get closer together, but they're not touching each other. But what ends up happening is the space between gets a little bit more compressed, and it gets harder and harder for blood to get through that area as well. But did you guys know this? I listened to this this interview on the radio one time, and it was a guy who works at the Miami Zoo, and he was talking about a chimpanzee. And for some reason, I don't know what he was talking about, but he was saying what's amazing about the chimps there at the zoo, by the way, they feed them a natural diet, right? They don't feed them like random stuff. They feed them what they would eat in nature. And what they said was that a chimpanzee, they wouldn't even know it had arthritis, and they would cut its knee open as an autopsy. At the end, they would see what they would call bone on bone. But they would have all this degeneration and arthritis, but the chimp never felt it. They were walking around like it was no problem at all. Okay, how does that happen? It's because when you have a whole bunch of acids inside of your bloodstream, and they're going through this small area, and inside of there you have things like uric acid crystals and things like that are really sharp, you're going to feel that, aren't you? Okay, it's going to be extremely painful, really sharp inside of your joints. Okay? But it's not the arthritis that's causing that pain. Makes sense? Yeah, it's all this junk that's inside of your blood. That's why, for example, I don't know if the person is here. No, I think it was Judith. She was saying she had knee pain for like 20 years off and on, over and over and over again. Day 2 of a water fast, it's completely gone.
As soon as she starts to eat, it's gone.
Yeah, as soon as she starts to eat food, it comes back again. Is that arthritis? Did the arthritis magically go away when she wasn't eating? You'll see that time and time again. You'll have somebody who has neck pain, they go to their doctor, and they'll do an x-ray, and they'll say, oh, it's arthritis. Right? Just because they have arthritis in their neck does not mean that's what's causing their pain. Alright? So that's what the myth comes from, and that it's bone on bone that's causing all of that pain and all that stuff. Okay? So, yes, go ahead, Rita.
Yeah, I have another question.
Yes.
Regarding the, is it acid buildup then? Because I have like, these muscles are really like hard.
Right? Yeah, it probably is. From years and years of holding your neck forward too, it starts to get really tense inside of there as well. Okay? And this goes to, we'll talk about weights and things like that. The more you compress these things or stretch these things, your body will compensate and start to put more fibers or more tension wires in there. Does that make sense? Well, let's get into this. Other things that we can do. How about yoga? Stretching out those ligaments more, opening those things up, practicing that motion. I was wishing Anna was here. She works for a new company called Stretch Zone.
What's
You
it
guys heard of
called?
them?
What's it called?
Stretch Zone.
Stretch zone.
Yeah. Anyone like to stretch?
Yes.
So I've always hated stretching, but at Stretch Zone they stretch you for you. You go and you look like somebody who's there and they just stretch you, which is cool. Laura like that. So I was wishing Anna was here. It'd be a nice little plug-in for her. Right? But just stretching those things out, taking time, and again, just even like while you're moving, you know, like doing like lunge walking while you're doing it, and stretching these things out, as opposed to being on a desk all day and closing in all day and doing this all day. Okay? Chiropractic, I hope you guys can see by moving this, you're literally affecting the entire structure. By the way, this is only talking about it from a biomechanical standpoint. Not even talking about the fluids that it's blocking inside your head or how it's putting pressure on your nervous system. I mean, it's pretty impactful. Even just structurally, how it can change every bit of DNA inside you without even talking about the nervous system and activating the flow again. Pretty cool, right? Movement. Probably the most important thing you can do is move every day, walk, run, jog, do things like that. And then finally, this is the coolest thing. Everyone talks about this. Anyone know what a squat is?
Yeah.
Okay. Especially when you load heavy weights on you, right? They say, oh, you gotta watch out for it because it's really bad for your knees and putting all this weight on you and doing it. Do you guys know, all the studies show the best thing you can do if you want to increase the cartilage between your knee joints, the best thing you can do, squats with weight. The more you're compressing, the stronger you're making. You're actually creating an electric field when you're doing this, and it actually builds the cushion every time. It's kind of like the more you use something, the more it builds up, right? The less you use it, the more you lose it, right? So think about the people you know who have really bad knees, right? A lot of times, either they're structurally off and they're using it, but a lot of times people get it when they're inactive for a while, right? So what's really cool about this is using weights and putting stress on you, stressing these things out is actually really good for your body. Make sense?
Mm-hmm.
Cool. Does anybody have any questions for me?
Yeah, you keep saying that it's changing your DNA, but I mean, is it actually changing the DNA, or is it changing the structure and how open or closed the DNA
There you go.
could be?
Thank you,
I
Jerry.
mean, it's like you can't change your DNA.
You have a cell, you have a nucleus, right? And then inside of there is where your DNA will be double helix. Okay? If we focus in on this, you get these little barcodes. Like a little binary language. And what these are, so let's say A, G, C, T, C, G, A, T, C, G, C, T. This is your little language. This might be a little blueprint right here. This right here might be a blueprint, which we call a gene, on how to make, let's say, blue eyes. Like a blue pigment. That's what you need, right? But see this red box over there? It's covered up. So my heart has this gene to make blue eyes. My heart doesn't ever make blue eyes. I hope it doesn't make blue eyes, right? So it keeps that closed off. So most genes inside of you are closed. Your cells, all the genes inside of you are blocked off. Nothing can get to it. What I'm saying, thank you, Jerry, is this doesn't change, but as you compress a cell and change its structure, you change its function. As you compress it, you start to open up a lot of these genes that wouldn't be expressed now will be expressed. Or vice versa, as you change the structure, other genes might close off that you want open.
Why would that be? I don't see why the change in this.
Well, when you change the structure of something, you change its function. So these are all proteins, these are all activated by energetic messages, and structural messages. I don't know if you remember that talk, but if you think about it this way, just from a biomechanical standpoint, this doesn't look like this. This looks like that.
Right.
And that's got strings to it,
Right.
attaching to the nucleus. And the nucleus has strings to it attaching to the DNA. And in there are strings attached to these things called proteins. So as you change the structure, you're going to pull tension and open up and move these proteins. It's literally like this. Imagine a string on. Imagine this is my DNA and this is a little code to make that blue pigment.
Mm-hmm.
This is protecting it.
Mm-hmm.
My protein. Now imagine a little tension wire, and as you pull, you start to open that up,
Mm-hmm.
right? And then as you take that away, it'll close it up again. Make sense?
That was a good demonstration on that.
I was on the fly too. That was cool. Kind of catch me off guard.
But I mean, yes, it makes sense, except that, if you, like your example of your heart is not going to make blue eyes.
Is that a good thing?
But it could.
Yeah.
Like, is it a good thing that when you compress the cells that they are?
So Jerry, I'm sure there's a mechanism in the infinite wisdom of the body of like, it knows all this stuff to adapt and to change. And don't forget, if my atlas goes out this way, I don't stay this way. My nervous system right away communicates to the rest of my body and tells other pulleys, other muscles to start like compensating, to balancing it out.
Why is that?
And that's the importance of the nervous system. Probably for what Jerry's saying too. It's like a protection mechanism. We're all living beings. We're all adapting. So you don't want to walk around like this. If my top bone goes out this way, my head will tilt, for example, like that. That'll cause brain damage, right? So instead of me walking around like this and pulling this muscle, my body will do this and counterbalance me.
So you're still not straight.
Yeah,
Right.
and you're still affecting the integrity of the structure, but because it's a living thing, it will adapt to a certain degree.
And it wants your head and eyes to be level.
Yes. Or else you get brain damage. Not fun. And it's probably because of that too. It's probably changing. It probably knows if you stay like this, certain DNA is going to express that you don't want it to. So let's adapt and do the best we can.
What about when eye color change? Like some people, their eye color will change.
Yeah. So that's a whole different talk, Prem. It's a whole talk about DNA and stuff like that. But essentially, you can change this. You can change the blueprint. When the blueprint is being made after it's already made, like the brown pigment, you can actually change that as well. There's multiple layers of when you can change your DNA too. So Prem is saying there are people, for example, they have multiple personality disorder. They have brown eyes, and they'll change personalities, and they'll have blue eyes.
Wow.
Yeah. Pretty crazy, huh? Yeah, we have crazy potential. There's a lot of potential we have inside of us in our DNA. But like I said, like if you look at our DNA, we have the same DNA. It's like 90% with most species on the planet. So I use this example a lot. You know that there was that kid who had a tumor in his brain and went blind at a young age, and he started to make sounds like clucking sounds, and he learned how to use echolocation. He literally developed part of his brain to have echolocation, so he could just literally skateboard and cluck and hear the vibrations back. And he learned that. That's in our DNA. When you learn about the DNA of our body, it's literally if you don't use it, you lose it. So we all have these potentials. Or you heard about the person who all of a sudden can lift a car to save their child. The environment is there. They release the hormones, so they unlock these parts of our DNA that make us super strong. And then when it's not needed anymore, they go away. Yeah, John, do you have a question?
No, I was just reminded of when you're talking about the strength of the structure of the studies that they've done on bees and the honeycomb.
Right.
And the shape of the honeycomb and how you think about how heavy honey is, yet those things are just fine, almost paper thin honeycombs. And they're that hexagon, that shape.
Wow, really good point. Really good point. Yeah, you see it, and that's what, it's funny, this guy does a really cool presentation about this, and he'll say, now that you guys know this in this basic shape, you'll see it everywhere.
Oh yeah.
It's all in nature, everywhere you go.
Get ready to trip out.
And it's just an interesting phenomenon, too. The more you squeeze it, the stronger it gets. It's just super interesting. And it's kind of the opposite, like a house, if you suck all the air out of it, what happens to it? It collapses, but these structures don't. And the guy goes on to talk about, like, something like a uterus or a heart is that when it's emptied of its fluid, or like let's say you push a baby out, it doesn't just collapse, it's actually still really strong. When you stretch something out like a balloon and you blow into it, you know how it gets thinner? That doesn't happen in these structures. And that's also true about your uterus, your heart, things like that. If you stretch them out, they stay the same thickness all the way around too. They don't get thinned out as you balloon them out. Pretty neat, right? Human body's pretty cool.
Oh yeah.
Any other questions? Did you guys like the talk tonight?
Yeah.
Well, it's super interesting, right? So, just to let you guys know, we have a breakfast talk Saturday, and our last Taco Tuesday we're doing Tuesday night. If you guys know anyone, please invite them to this last couple ones, okay? I'm trying to think what else. Next week, the scoop on poop.
Yeah.
Laura?
No, I'm not gonna be
Expect you to be here for that. You're gonna love it.
That's why I'm here tonight.
All right, fair enough. Awesome, guys. All right, hope you guys enjoyed. Love you guys. Thank you.